professor, or was a professor, here in the Department of Geology and Geophysics since 1977. He's now retired. And comes back because he wants to talk to this class, and we really appreciate it. He received his bachelor's at University of California at Santa Barbara, his master's in geology at University of Oregon in Eugene, and his PhD in geology at University of Otago in Dunedin, New Zealand. He has field experience around the world, doing field work here in Hawaii, also Canada, New Zealand, Iceland, the Marquesas, Easter Island, and many, many research dives on submersibles. So here to tell us about the geology of the Hawaiian Islands, join me in welcoming Dr. Sinton.
Interesting. My name was on this slide, but it seems to have gone away, so I'm not sure what that means. I hope we don't have other issues like that as we go on. I've got a lot of ground to cover. Basically, I'm going to talk to you a bit about the overall, what we might call geological province of Hawaii. It's more than just the islands. It's more than just a volcano here and there. And so we refer to this as the Hawaiian swell. And I'll tell you what I mean by that, why we call it that, all that kind of stuff. And we'll talk a bit about the overall general context of the Hawaiian Islands and the Hawaiian swell. And then I want to talk a little more about Hawaiian volcanoes individually, how they evolve, how they form, and how they're modified. So that's a lot, but we'll get through it, I think, just fine. First point I want to make to you is that if you look at I like to start with something we're all familiar with, pretty much, which is the main islands where we live. You might be less familiar with the submarine part of these islands, but in fact, that's one of the great areas of progress we've made in the last decades, is the mapping around the submarine parts of the islands and what we've learned from. One thing, if you look at the Hawaiian Islands, that is apparent is that you have, they're not equally distributed, they're not like a strand of pearls, one after the other, but they are in clusters. The Big Island cluster down here is a mixture of several different mountains, which are each individual volcanoes. The Maui Cluster is separated from the Big Island by the Alenuihaha Channel. We sometimes refer to this as Maui Nui, Greater Maui. The Oahu Cluster is all of this stuff up here, Kauai, etc. These, so the Big Island, as you probably know, is at least 5 separate You know what? This is an older version of this talk. That's okay. We'll make do with it. I don't know where I put the new version. That's why my name's missing. But anyway, we'll deal with this, and it should be okay. I wonder how much older it is. Okay, we'll do the best we can. All right. So there's 5 principal volcanoes on the Big Island. You already know their names. 3 of these have had volcanic eruptions in the last 250 years or so, so-called historical period in Hawaii. The modified version of this talk also talked about Loihi, which is down here, so a 6th volcano that, if it continues to grow, will become part of the Big Island, probably, already is in some respects. And it has also had eruptions in the last 200 years. In fact, almost certainly had eruptions in the 1980s. The Maui Cluster, Maui Nui so-called, is 6 different volcanoes at least. And they're sort of numbered up here, 3, 4, 5, 6, which are these principal volcanoes. So there's at least 6. Some people might add a separate volcano on Penguin Bank, but that's unconfirmed, not obviously true. But interestingly, all of Maui was at one time a single island, although now it's 4 different islands. Those 6 volcanoes make. They were a single island a little over 1 million years ago, rather like the Big Island. And the Oahu Cluster, shown here as an assemblage of overlapping volcanoes, is at least 3 volcanoes. I wonder where my other version of this talk is. They are labeled on the other version, but this one we call Kaena. It's offshore Waianae. There is an older volcano out there, the Waianae volcano here, and Ko'olau volcano here. So there are at least 3 major volcanoes that make up the Oahu Cluster. Not 2, just the 2 subaerial ones, but in fact 3. And although only 2 of those are currently subaerial, Kaena used to be. We know pretty much where the submarine to subaerial transition is on Kaena volcano, the offshore one. And Kaena was about almost 1,000 meters high. I like to think of Kaena as something like Kaho'olawe in its scale, its size, and its height above sea level. It was about the similar height, and that was about 3.5 million years ago when Kaena was subaerial. So we have these 3 volcanoes then that are kind of stacked up like this along the Hawaiian Chain. The
We have the last presentation from last year. Would that be better?
no, this is better.
This is better?
Yeah.
Sorry.
I modified it, but I don't know where it went. And then when I copied it to my thumb drive, I grabbed an older version of this talk. But, so this is the overall version of. Are these too bright? Are the lights too bright? Can we dim them a little? It might be easier to see. The overall Hawaiian province, if you like. So this is a point that you probably already know. What we've been talking about is just this end of the Hawaiian Chain, the principal islands, what some people call the main Hawaiian Islands. That's better. Thank you. But as you probably know, the main islands sit at the southeast end of a long chain, something like 8,000 kilometers long or so, that extends all the way up. There's a bend between the so-called Hawaiian Ridge and the Emperor Seamounts, and another bend up here, and then the province disappears in the trench near Kamchatka. We think of this as all part of Hawaii, a long history of Hawaiian volcanism that extends all across the Pacific Basin. The principal parts of the chain are commonly divided up into the Hawaiian Ridge and the Emperor Seamounts. That's just some terminology for you. So it's long. It's also broad. When we think about Hawaii, a geologist doesn't just think about the Big Island or the volcanoes that sit above the sea, but in fact, in this dimension, it's also a broad province. And this is what we call the Hawaiian swell. If you look at the bathymetry offshore, deep blue colors are deep, and then there's this paler color that is shallower. Then it goes deep again, right close to the islands, and then you come to the islands themselves. So we divide the Hawaiian swell. It has been divided or described in terms of the arch, this broad arching region, which is out here and down here. Up close to the islands is the deep or the moat right around the islands. And then you have the so-called Hawaiian Ridge, which the islands sit astride the Hawaiian Ridge. So when we think about the Hawaiian swell, it's the whole structure. A structure that is, this is 550 kilometer scale, so this is something like 600 or 700 kilometers across the whole of the Hawaiian swell. What is the Hawaiian swell? Why is it there? Why is it not just this string of pearls? What is this whole structure about? Well, these are some really kind of lame cartoons, but they're meant to illustrate what this structure is. Partly this swell is a thermal swell. That is, as new magma, new material is added to the crust from below, the so-called Hawaiian hotspot that feeds this, the crust, or the lithosphere, swells and expands as hot material is added to it. And so the whole thing gets broad and shallow from thermal expansion. But there's also this process that we call flexure, or bending. As you load a soft plate or an elastic plate, you get depression right around the volcano itself and arching out away from the volcano. So in this view, the Hawaiian swell is this whole structure. This is the arch, this is the moat or deep, and of course the Hawaiian Ridge that sticks up here. So you got a combination of thermal effects going on and bending forces taking place as you load a plate that's been softened by thermal expansion as you heated it up. I have a much better figure in the new version. The main point to make here is that the islands are not distributed equally along this chain, but rather there are isolated volcanoes. They're not equally distributed. For example, if you look at this Hawaiian Ridge, there's almost a gap in it right here when there don't seem to be any volcanoes. Then it got very fat again. Another gap up here. So basically you can say that whatever has made this Hawaiian Ridge and the Hawaiian swell, it has not been equally productive in either space or time along this whole structure. There's been a lot of variation that's taken place, but it's not been a very regular process. They generally get deeper. Here's that gap, a couple of those gaps I was talking about, but overall things tend to get deeper as you go in this direction. If you look at the heights of various features along the Hawaiian Ridge, going all the way out now, some 6,000 kilometers or so, you see the very high islands are all at the southeast end of the ridge. They come down this way and eventually are all submerged in this region. What's going on here? Why does this happen? Why do things get either less high or deeper as you go? Erosion. Erosion's part of the story. Certainly there is erosion taking place all along the islands. Anything else? Yeah. Drag. I'm not sure if I follow what you mean by the dragging process.
Like isostatic, something that's sinking.
Sinking. This is what we're subsidence? Basically, they sink. And this was a part of the talk that I worked on recently that probably didn't make it into this slide, but we'll talk a bit about it. If you think about subsidence, remember when we loaded the plate, we depressed it right under the Hawaiian Ridge and then it flexed, and we were talking about flexure? That is a kind of subsidence that can depress the plate. So volcanoes actually sink. Islands sink. They sink into the underlying region of the Earth we call the Asthenosphere, the soft part of the upper mantle. And so a lot of this is actually subsidence. If we put a subsidence curve on here, we see that it looks something like this, and it really has two different processes that are dominating a subsidence curve. In this part of the Hawaiian chain, where all the active volcanism is and the plate is very soft, this is mostly subsidence that can occur on rates of as high as about 2.5 meters per 1,000 years. It's fairly rapid subsidence in this part of the curve. And then out at this end, the plate is no longer soft, so you don't have that kind of subsidence taking place, but the plate is older and it cools and it contracts. So out at this region, you have very slow subsidence on more like a tenth of a meter per 1,000 years. That is the subsidence rate out at this end of the chain. Slides are out of sequence too. Well, I'm sorry about this. Here are some cross sections across the Hawaiian Ridge. Now I've done it. There we go. That is a depiction along the Hawaiian Ridge. So this is from Kauai going to the southeast toward the Big Island. These are some drawings that were made by Jim Moore years ago, trying to show the effect of subsidence as each volcano forms on top of the old one. Everything sinks down underneath it. So these lines are isochrons in millions of years, and you see they all dip toward the youngest lobe. And if you look back at, there are various things that he's shown in idealized lines on here on how much subsidence has actually taken place, but the point is that by the time you get to Maui or so, most of the volcanoes have subsided at least 3 or 4 kilometers, 3,000 or 4,000 meters of subsidence. So let's think about that for a minute. Waianae, Mount Kaala is the highest point on this island, a little over a kilometer high, 4,000 feet or so. Was it ever as high as Mauna Kea or Mauna Loa?
Probably.
If it subsided 3 or 4 kilometers, quite likely. And actually there is some evidence for that. There's an amazing lack of plant fossils, plant molds in the lava flows of Waianae, which suggests that most of the lavas we see out of Waianae were above the tree line when they formed. And now they're down in a few hundred to a few thousand feet, but not when they formed. So I think they probably were. And that the reason it's low now is partly, at least, subsidence. What about erosion? Well, actually, I think there's a lot of original topography out on Waianae. We haven't taken 3 kilometers off the top, nowhere near. In fact, we're very near to original topography in Waianae, but mostly it's sunk down several kilometers. It's subsided. Okay, so we think we know something about subsidence, but look here. There's a region like 1,500 kilometers or so long, where all the edifices are exactly the same height. What's going on in that region? If this is the subsidence curve, what is it that keeps all of these guys from not subsiding below sea level?
Growth. Like growth of corals.
Growth of coral, exactly. This is reef. Those are all reef islands. In fact, those are mostly atolls. And so how do you make an atoll? Atolls form when the reef that's growing on the edges of the islands, as the island is subsiding, if that reef growth is fast enough to keep pace with subsidence, then it will stay right at sea level no matter that this thing sinks. This is an idea that goes back to this fellow Darwin. You've heard of him. He had one or two good ideas, and this is one of them. The whole formation of atolls, he figured this out, that they must be the superficial carapace on a subsiding volcano. And I proposed this in the 19th century, and we tested this hypothesis, in fact, more than 100 years after that by drilling into Midway Atoll, where there's no volcanic rock on the surface. That drill core eventually encountered the volcano at depth. I don't remember the exact depth at which it reached the volcanic underpinnings of Midway Atoll, effectively confirming Darwin's hypothesis for the origin of atolls. Eventually, though, they sink. So you have this region of active volcanism and strong subsidence. You have this region of atoll formation and growth, and you have a region beyond about here where all the features are submarine. So those are drowned atolls, we know, because we can visit them, drill them, and they had coral on them, but it all drowned. It's all dead. It's gone below sea level. So basically we have a situation where we have seamounts or drowned atolls that occur when reef building does not keep pace with island subsidence. But I told you earlier that part way out there of the slow part of the subsidence curve has a magnitude of about 0.1 millimeters per thousand meters per 1,000 years. Corals can grow faster than that. Corals can grow much faster than that. So how do you drown an atoll? Well, you're right at sea level, so you can have a little bit of wave erosion, but that'll keep the island within the photic zone where corals can still grow. Must be more to it. Well, maybe I lied to you. Maybe I lied to you about coral growth. Coral growth isn't a single number. The rate at which coral grows depends on a lot of things. How deep a water it is. Anything else?
Temperature.
How warm the water is. Yeah. Times of rapid climate change, you can drown things because you have big rapid sea level rise. We're no longer just talking about slow subsidence. There can be big pulses. Where is the end of the atolls and the beginning of the submerged seamounts? It's right about up here along the chain. Here's the Hawaiian Chain. And the problem is that whole transect that I was drawing for you is moving up to the northwest, west-northwest. And so these things where atolls are forming are right in here where the water is still fairly warm. But eventually they migrate up into colder and colder water where coral growth rates are much less. And even ignoring things like rapid climate change or whatever, eventually coral simply cannot grow to keep pace with subsidence if they're moving into colder and colder water. Now, exactly where that is will depend on many other variables, but at least we know that probably explains why you eventually drown atolls. Things get older to the northwest. I haven't really emphasized this yet, talked very much about it, but we know it's true. This again is a 19th century concept that people looked at the Hawaiian Islands and said, man, Mauna Loa looks younger than Kauai. And a whole series of other observations along the way. And if we just take a few islands in the chain, from Mauna Loa, Mauna Kea, out to Kauai, the oldest known rocks have ages that look like this. Don't put too much on that because we don't know that much. We never know the oldest rocks of an island because they're buried underneath in the middle and the bottom where we can't get at them. A lot of islands are rather poorly dated, etc., but these are the data we have, and you see that they go from the oldest rocks on Mauna Loa that we know about are about 300,000, and those on Kauai are about 6 million, and there's a progression. This is not the same as saying the last known activity on these islands, and if you look at that kind of thing, you find there's some interesting reversals in the trend. For example, Ko'olau has had eruptions less than 100,000 years, even though it's a much older volcano. And on Kauai, there's actually some eruptions there that have occurred in the last 500,000 years or so, even though Kauai started 6 million years ago. All I'm doing here is kind of highlighting some of the complexities in volcano growth, some things to think about in these terms. The overall trend of edifice ages along the chain looks like this, going out full 6,000 kilometers or so. It's pretty striking. It's a pretty regular trend going all the way up, even though there's bends in it, and there's a lot of problems with the dating that could certainly be improved. But one of the conclusions we can draw from this is that whatever made the Hawaiian province, it's been going on for something like 80 million years, getting up to some of the oldest things way up at the end of the Emperor Seamount. So Hawaii's been around on this planet for quite a long time. Apparently the motion of the Pacific plate along the chain has been fairly regular. That is, you can fit most of the points on this line to a single line. In fact, it's not just a crazy scatter. So it's been a fairly regular process. Another point that I wanted to mention is that bend then, if you think about this as simply being an expression of volcanism as a plate moves over a hot spot or a melting anomaly, then the Hawaii Emperor Bend must be a change in plate motion. So that assumption or that concept implies that the hot spot itself is fixed and the plate is simply moving over it. Like many things, we're finding it's probably not that simple. Hot spots can move around a little bit. They don't move in the same way that plates move over the top of them, but nevertheless, that's the basic concept. And we're not alone. Here's the Hawaii Emperor chain. There are other hot spots in the Pacific region that fit on this map. Can't read these, I know, but I've listed some of these, which are also considered to be hot spots expression in the Pacific. And maybe the Louisville also has a bend in it, kind of like the Hawaii Emperor Bend at about the same time. In the Cook-Austral chains, people think this is an expression of that with another bend in it. So these are the kinds of arguments that lead credence to the idea that hotspots are relatively fixed and plates move over them. Not all hotspots are in the oceans. Some are in the continents like Yellowstone. Not all of them are on the Pacific plate. Here's two on the other plate, on the Nazca plate, in this case as well. Okay, I'm going to change gears now. And I'm going to talk a little bit about volcanic evolution or island evolution. And one way to introduce this topic is to take two volcanoes that are very similar. They're neighbors. They're right next to one another. They differ in elevation by an insignificant amount, a few tens to hundreds of feet. In fact, they're both about the same height, etc. Yet they look pretty different. Mauna Loa is very smooth. Mauna Kea is kind of bumpy and a little bit more irregular. If we go to the surface, Mauna Loa has these fresh lava flows, mostly pahoehoe lava, very smooth kind of lava that mantles the surface, whereas Mauna Kea is much rougher surface, much more cinder, much harder to find individual lava flows to map them out, even though it can be done. And of course, the summits are very different. Mauna Loa has these calderas, this big depression and pit craters. Here's Mauna Kea in the back, which you know is mostly surmounted by cinder cones, and you can drive up it where it's very hard to drive up Mauna Loa. So they're very different looking animals, if you like, in many respects. Why are these two volcanoes side by side on the Big Island, same height, but with such different character? This idea comes from Harold Stearns, the concept of Harold Stearns. He mapped the Hawaiian volcanoes and he described these things, and he went through and had the concept that volcanoes evolve or they age, what he called life stages of Hawaiian volcanoes. And this is a more modern version of this, where things start at below sea level, they grow up to make a main shield stage volcano, which is what Mauna Loa is now. Eventually, they go into the old age stage, which is where Mauna Kea is now, and some of them can become rejuvenated later on. And I'm going to talk a little bit about some of these different features, but the tale of two volcanoes, comparing these two, is comparing a mature active volcano to one in decline, an older volcano that is starting to decline. And in this compilation, there are a number of things that go on with this, the formation of calderas and rift zones and landslides and magma chambers, and all of these things contribute to this process. Yeah?
But even though Mauna Kea said it's in decline, it's still a little bit higher than Mauna Loa.
It's slightly higher. Yeah. The heights, it turns out, of volcanoes is not it's not diagnostic of very much. Keep in mind that volcanoes form on the flanks of older ones, and in fact, Mauna Kea is built on a very big Kohala. You might not think of Kohala as big, but it was a really big volcano, and Mauna Kea grew on top of it. It didn't grow from the deep ocean up. It got a boost. So it turns out heights are not so important.
Oh, so Mauna Kea is taller because it's actually sitting on top of another.
It's sitting on top of Kohala. But Mauna Loa may be sitting on part of Hualalai. There's a lot of things we don't know. But yeah. Height's not the most important. I thought you were going to say, but Mauna Kea is still active, because it is. The last eruption was about 4,000 years ago. There will almost certainly be more eruptions on Mauna Kea. It's not dead, just old. Don't equate old with dead. Okay. I'm gonna jump around and to more to the way I reorganized this talk. So I'll just a lot of them are the same slides. Here, in thinking about this in these life stages, here is a kind of idealized growth history. So you can think of a volcano first starting here, maybe in the submarine stage, and then there's a period of very rapid growth where it emerges above sea level, and then there might be a period of several 100,000 years where you have sustained volcanism that is the so-called shield stage. And examples of volcanoes currently in this shield stage are Kilauea and Mauna Loa today. They're both very active, as you probably know. Mauna Loa in recent time less active, last eruption 1984, but everyone thinks it's going to go again. And we're just not sure exactly when, but it's inflating and it's being fed, and it's still going. So you can think of this as the shield stage. And then a long tail of decline can occur in Hawaiian volcanoes where they slowly wane. So Mauna Kea is probably somewhere out here in this picture, whereas Mauna Loa is still maybe just coming over the edge here. This is their height. This would be for an idealized volcano that starts from the seafloor, but I've already told you that almost none of them do that. Cayena did, but most of them start on the shoulder of a neighbor. Actually, within clusters that I talked about, the first one might start from the seafloor, and then everyone else builds on the shoulders of it. But this would be height, and it only decreases in height very slightly from its prime time. It's just not growing as much anymore. Okay. We don't need to look at these details. Let me take you back through some of the stages of volcanism again. The shield stage is the dominant stage then in terms of growth. It's the dominant period where production is at a maximum, the eruption frequency is at its highest. And I'll just show you a few depictions of this, but this dominates the volume. The idea is that ideal Hawaiian volcanoes in the shield stage have a summit caldera, and then these long things we call rift zones, sometimes with a minor third one. Rift zones are an indication of the plumbing system of Hawaiian volcanoes, the way magma rises up beneath the summit caldera and can be fed out along these rift zones so that you can have flank or rift zone eruptions. And you probably know that that's what's been going on Kilauea since 1983, when we started a rift zone eruption out at Pu'u'o, and it's still going today from that kind of operation. The lava tends to be fluid, pahoehoe type lava that you are familiar with. Calderas are a feature of shield volcanoes, these summit depressions. They're very dynamic. They change on very short time scales, years, even months sometimes. They change in two ways. The walls can collapse, as Waldron Ledge did a few years ago, well, quite a few now. Waldron Ledge is up here. So they get bigger by collapse on the margins, but they can also change by infilling with younger lava flows. So here's some maps of Kilauea made from 1825, 1944, and pretty much now, or at least a few years ago, within the last 10 years, and how they change. These are this depiction of the rift zones, the way this in cartoon view, the way magma is fed out along rifts. But we know what this looks like. They look like dikes. They are dikes. Dikes are the plumbing system of Hawaiian volcanoes. They show you the transportation of magma from the central part, or from depth up to the surface, or out along the edges of the rift zones. And this is on the Mokulua Islands. On this island, so this is part of the rift zone of Ko'olau volcano, which is a dike complex. I have a better figure than this now, but anyway, this shows the dike complex of Ko'olau. The old caldera region was back here, and these dikes are feeding the rift zone of Kilauea. Now I'm going to go back. The transition from shield to post-shield comes from mapping. You can see it. You can go out in the volcanoes and you can see the transition. So here's one of the best examples I know of is on Molokai. This was on East Molokai. You can see that there are the lower part of this mountain are these thin-bedded red-brown lava flows. Here they are in the cliff. And they're overlain by much thicker-bedded, lighter-colored lavas here that are telling you something about a fundamental change in the volcanic activity on this volcano. And this is what Harold Stearns called the shield to post-shield transition. And it's mappable on lots of different Hawaiian volcanoes, this shield to post-shield transition. This is it at the Mo'o area of East Molokai, on the north shore of East Molokai. You can also see it on the Waianae, shield lavas at the base to post-shield on the top. Think of this as Mauna Loa, Mauna Kea surfaces. So the idea would be that Mauna Kea now is in this old age or post-shield stage, but it went through the earlier shield stage down beneath.
So basically the lava changes.
Pardon me?
The composition of the lava changes.
The composition of the lava changes. And people like me who study the chemistry of lavas will tell you that the degree of melting declines. Also, the depth of magma evolution is deeper in the volcano. So there are a lot of magmatic processes tied up with this shield to post-shield. But all of them represent or reflect the migration of the volcano away from the center of the hotspot. So you're out on the edge, growth rates come down, the melting of the underlying mantle is less. They tend to be more differentiated. That's why they cooler temperature. That's why they change color. Yep.
So you said Mauna Loa that's erupted in 1984, yeah?
Yep.
So which type of lava did that eruption produce?
Very similar to the 20,000 years before it. It's good shield lava.
Okay.
It's still high degrees of melting. It's don't make too much of the difference between 1984 and today. This is kind of insignificant to a geologist. Mauna Loa has been very productive over the last few hundred years. Certainly in the last 50 years or so, it's been less productive than Kilauea, but it wasn't very long ago that it was equally productive. Now I'm confused where I'm going, but the other aspect of Hawaiian volcanism, and actually I should tell you probably the least well understood aspect of Hawaiian volcanism, is this so-called rejuvenated stage. There are places where you have much younger volcanism that clearly postdates a long time break. Here's the Cocoa Rift, and in this case you have 2 to 3 million year old Ko'olau volcano and 100,000-year-old Cocoa Rift things. So we're looking at a 2 million year hiatus in volcanic activity in that particular area. That's the concept of rejuvenated stage. What causes it? Good question. I'm not going to try. I don't really have time to go into the different hypotheses, but I'll tell you, this is the least well understood aspect of Hawaiian volcanism there is. Why some volcanoes come back into activity after 1 million years or more of hiatus. Not well understood. Let's talk a little bit about Oahu. Well, actually, let's go back one. Reefs grow around Hawaiian Islands all the time. They want to grow around Hawaiian Islands all the time because it's pretty warm and it's a pretty good place for reefs to grow. But they want to grow around the big island too, but with fresh lava coming down, it wipes them out periodically. So you should think of reef growth and erosion as ongoing processes. It's not like they kick in, but when volcanism slows down, these processes become more apparent, and you can see them better. Here's some reefs forming on the side of East Molokai because there's been no eruptions on East Molokai for over 1 million years, at least on the south side of Molokai. I just want to show you a few geomorphic features of Oahu since we live here. There are river-cut valleys like Manoa, Palolo, all the main valleys. These are river-cut valleys. Pearl Harbor is a drowned river valley, an estuary. There are sea cliffs that we can find on the island. These are all erosional processes that have affected this island. Former shoreline must have been around here. The Cocoa Rift came up offshore. That's why it was explosive. It interacted with seawater. I want to say a few words about mass wasting or landsliding. When we talk about erosion, some people would say mass wasting and erosion are different because erosion is always slow. But I don't buy that. Erosion is really fast, in fact. An island can sit around, you know this very well, it can sit around for years and nothing happens, and in one big storm you can do more damage in a few minutes to a few hours than you did in the previous decades. Erosion can be very fast. And the fastest kind of erosion, or changing, is by when things move en masse, so-called mass wasting. Here's a landslide in Palolo Valley. It was caused by some old quarrying, and then it's started sliding down, took out, this used to be all houses. But it's a very common process, and this is the way valleys widen. You might wonder why, how do we make such broad valleys from these little mini streams? And the fact is they cut down, and then the walls all cave in from the sides. So the way valleys widen is by mass wasting. And we now know that there are some huge submarine landslides that have affected the Hawaiian Islands. And here is a map showing you the distribution of these. There are a couple of different types that aren't so important, but you can see that these islands degrade by mass wasting, by landsliding. This is one of the principal ways they evolve. I'll talk a little bit about this one. This is the Nu'uanu debris avalanche. It's the largest one we know about. These are some dimensions. It's huge. This is Tuscaloosa Seamount, this monstrous thing. Look at the size of that single block compared to Oahu. This is a landslide block. This thing became detached from the edge of the edifice and went sliding off into the outer region. This was a huge, this is the axis of the moat. So all of this debris actually went uphill underwater by a long period. So pretty amazing thing. The Polly is not the landslide slip, it's offshore, way up here. I'll skip, well, I'll just mention that on the Big Island we have active landsliding going on. These are GPS arrows showing that it's all slumping off. A lot of that slumping is because it's on the edge of Mauna Loa. I'm going to skip this part and just talk to you about, well, we'll close it there, but I wanted to say that of those big submarine landslides, there are 17 in the Hawaiian Islands that we've recognized that represent 5 million years of activity. So that gives you about a recurrence interval of about 300,000 years or so. But there's got to be lots more of them that we don't see because they're buried by younger deposits. And if you take it up along the whole Hawaiian chain, you might get a 500,000 year recurrence, but again, that's a minimum. So they're not common, they're not frequent, but it's important to keep in mind because they do pose a significant hazard, even though it's uncommon. Okay, sorry for the disjointed part of this, but I'll be happy to answer any questions.